Hi everyone. So in this video we'll study an approximation of the cost function, and that approximation will give us actually a very good interpretation of L2 regularization. But like any approximation that facilitates theoretical analysis, it's very important to remember what exactly did we assume through this approximation. So what we will do is that we will consider the minimum or the optimal value of that cost of the unregularized cost function without L2 regularization. And let's say this value of the parameter setting that gives the optimal the minimum value of the cost function without regularization, let's call it omega star. Then I will approximate the cost function around omega star by a quadratic function, right? And let's see why, the reason specifically we are doing this here. But in general, quadratic approximation is one form of a convex approximation, and usually when you have a convex function, it's easy to find the minimum by just setting the gradient to 0. So it's very common to have these convex function approximation around a certain point of interest. And here the point is the minimum of the unregularized cost. So to do that, we use Taylor series approximation, and you're welcome to check out the details of that online. Wikipedia can basically give you enough information, sufficient information for our needs here. So the approximation of the cost function will be given by the cost at omega star plus some factor of the gradient of the cost at omega star, but because we are assuming this is a quadratic function, the gradient at omega star is 0, right? Plus some function that will depend on the second order derivative information, which here in the multidimensional case is given by the Hessian matrix, and this Hessian is evaluated at omega star. Right? So the gradient at omega star is 0, so you don't see a first order derivative term, and the second order derivative term is half omega minus omega star transpose h omega minus omega star. So it's quadratic in omega times the second order derivative information of the cost with respect to w evaluated at omega star, meaning that you have the Hessian matrix expressions of second order derivative and then you evaluate at omega star. Now, also note that h is positive semi-definite, and that means at omega star, right? So what does it mean that the h is positive semi-definite? It means that the second derivative is positive in all directions, right? And that's basically a function of the minimum, right? So if I am at the minimum of a function that's convex or quadratic, then I know that the first derivative is 0, and the second derivative, this first derivative is increasing in both directions, right? So I have to have the second derivative being positive in both directions around the minimum, and that's what it means that the h is positive semi-definite, because the second derivative, the derivative of the function is increasing in all directions around the minimum, right? So then we want to find the optimal, so we set the gradient to be equal to 0, and the gradient of the unregularized, so I didn't add regularization factor yet, is basically the minimum is given by the gradient is h times omega minus omega star, right? Because here this is quadratic in omega, so the gradient is given by 2 times this times omega minus omega star times h, which is a constant in this case, right? Because the h is evaluated at omega star, it's not a function of omega anymore, right? And then we add the regularization and see the effect of the regularization on the optimal solution. So if I add the regularized term, so as we saw last time, it will add a factor of alpha omega to the gradient, right? So then we will have then the gradient will be equal to h omega minus omega star, and then we have the alpha omega tilde, which is the omega tilde now is the new minimum with L2 regularization, right? So the new minimum will be given by h. I replace omega by omega tilde by h omega tilde minus omega star times plus alpha omega tilde. And the alpha omega tilde is coming from the gradient with respect the gradient of the regularization added term, right? The L2 regularization added term, and H omega tilde minus omega star is the term that we had here. We are just evaluating at the new minimum. So we replace omega by omega tilde. Now, with simple manipulation, I could have H plus alpha times the identity matrix times omega tilde equal the other side will have H omega star. So I move H omega star to the right side. And then, since H is positive semi-definite, it's also invertible. And it's still invertible if I add the identity matrix to it, because the identity matrix is full rank. So, omega tilde will be given by H plus alpha I inverse times H omega star. Right? Now let's decompose H. Since it's positive semi-definite, I can have a singular value decomposition of H, right? So I can decompose H into a function that's Q, right? And that function basically has orthonormal basis of eigenvectors of H. So that function is a matrix, Q, and that matrix is a vector of single norm, of unity norm basis, right? And that basis represents the directions of these bases represent the directions of the eigenvectors of H, right? So you have Q, and then the omega, which is the scaling factors or the eigenvalues along each eigenvector, times Q transpose plus alpha I inverse. So I replaced H by Q lambda Q transpose. Q is the orthonormal basis of the eigenvectors. Lambda is the diagonal matrix of the eigenvalues. You can think of it in terms of vector spaces, and you can dig in more detail in this if you want, as Q gives me the directions, the new basis that H gives me, and lambda gives me the scaling factors, the coefficients across each basis. And then I replace H here as well by Q lambda Q transpose, right? Now, I could rewrite this as Q lambda plus alpha I Q transpose. Why? Because Q transpose is simply the identity matrix. So this is Q lambda Q transpose plus Q alpha I Q transpose, which is the same as alpha I. Right? Now, if I do the inverse of this thing, how do I do it? I take the last one and invert it and put it at first. So it becomes Q transpose inverse. And because Q is a matrix of orthonormal basis, right? So the orthonormal means they are unity norm, each of the vectors, and then in the matrix, and they are orthogonal to each other. So Q transpose is the same as Q inverse, right? So Q transpose inverse is the same as Q. So that becomes Q transpose inverse becomes Q here. And then I have lambda plus alpha I inverse, and then I have this Q becomes Q inverse. And Q inverse Q is I, so I can remove them, right? And then I have lambda Q transpose omega star, right? So just to elaborate, this step can be written as Q transpose inverse, lambda plus Q inverse, and then Q lambda Q transpose omega star, right? So that's an intermediary step, and then I have the final step here, right? Now the final thing that we have is this Q lambda plus alpha I inverse lambda Q transpose omega star. Next time we'll discuss the interpretation of this expression that we had for the final solution. But just to give you a glance on what we will have, think of this Q transpose omega star as a projection of, remember what's omega star? Omega star is the minimum of the unregularized function. And Q is a basis of eigenvectors of H, right? I project omega star along this new basis of eigenvectors of H, and then we do some manipulation, right? So first I project omega star in the new space that is defined by H, And H, remember, is the Hessian with respect to omega evaluated at the unregularized minimum. Next time we will dig into more details into this expression and see what's the interpretation of the optimal solution obtained by L2 regularization in light of this approximation. Thank you.